Okay, today we'll be implementing WHFast. This is gonna be harder than I thought because of, the fact that Rebound is GPL licensed. So therefore, GPL means I can't copy it, even algorithmically, which was something I assumed would be true earlier. So that's a big issue. I don't want to put this in GPL. I put this in as MPL. So yeah. So this is gonna be manually implemented. And no, I don't care that these are in the code. I do not care. He has better things to do in life than DMCA, a random project on GitHub. He's a literal physics professor. He has more important things to do. But if I put the whole WHFast implementation in here, that might stretch the line, and yeah. Alright, so I just made it. Yeah, so I just made Gemini summarize this and give me an algorithm to, half implement it at least. Okay. State vector define this stuff. Yeah, we already have all that monstrosity. First point it to 1 to n minus 1. We say vi times what is basically just, acceleration, which gonna have a very significant impact. So if I have to do check something. It's been a long time since I opened Excel. Yeah, wait, it literally creates that. So let me just wait. Did I just accidentally create an Excel.app file? So nvim includes gravity.hpp. Okay, so basic Jacobian compensated. Okay, now I have to go to nvim include /whfast.hpp. Just quit. Okay, don't write. It's gonna write an empty file. Okay, now there's nothing in there. So what is integrator.hpp? So gravity method. Gravity should be just gravity method basic. And epsilon should equal this. Just your standard setup. I'm going to add more as necessary. src / WHFast.cpp. Okay, now WHFast step. Okay, if I get to here, G times MJ times this for each planet 1 to n minus 1, you do delta t divided by 2 times J if it's not I or 0. So this is literally just calculating the acceleration. So if I just go into here and the acceleration is just update Excel, and we have to particles, and in here we have to update Excel, and I'm just gonna make it get a const reference to const WHFast. WHFast. Or just in the, let's get it, give it the gravity method actually. And now, not pipe. Oh my! The autocomplete on this is terrible. Particle store particles. All right. This is going to be easy. This is probably just going to be a switch. So, switch method. That would be gravity method colon basic. You have Excel. A better solution here. I have to include gravity. That's if I can. Yeah, I forgot case. I've been doing too much Rust lately. Anyway, if I hit break, and here is order. Excel basic, particles, and epsilon, which should be epsilon 2, which epsilon 2. It's very similar over here. Or just gonna be just pasting compensated. Where we just Jacobi, and you also have to set it to Jacobi here. Default break. Not sure that this, no, the 66 warning just spawned, but yeah, I guess that's, we are just gonna ignore that. And yes, I know there's no such thing as acceleration. Let's just pretend that's a fine. Let's just pretend, yeah. And if I, now I should be able to just say, what do? We say, so kick it's delta t divided by 2 times what is basically just acceleration. Okay. So we just I think, yeah, I know it does technically do it for 0, but does it break the math? Does it? I already have functions to, yeah, I already have functions that just straight up return 0. I should have also added the star to to calculate acceleration, and yeah, as you saw last video, I also pre-prepared a bunch of Jacobi transformations. Yeah, so like this is gonna be a bit easier. Okay. I kind of screwed this guy up from talking. Functions to calculate acceleration. Yeah, but they include the star and effects. Yeah. Yeah, that might cause an issue. I don't know. Yeah. Okay. So just the kick is just okay. Need an interaction acceleration. Okay, so that seems trivial to do. I guess that's easier enough to do. I guess it works. Yeah, this won't be that complicated of a procedure. So let's get to work. If I update the acceleration with gravity epsilon times epsilon and particles. Okay. Now we just take the star. If you look at the math, it's like clicky. So say if we have it's gm1 m2 over r squared. Since we already know this, it's gonna force exerted by the star on the planet, we divide by m2, which just leaves this. We just subtract this. So we have just the mu of the star divided by that. Seems pretty trivial. So it'll be, so if we look, vec3 star excel should equal, and the acceleration, so a acceleration function also already affects all bodies too. So yeah, that might also be an issue. I don't know. It could be moving the star around. That's quite literally what I'm doing. Then this basic code. Okay, so let's just continue with this. That it's gonna have, but it's just basically just gonna. Yeah, that's actually I don't think it's fine for the acceleration. Actually, we just pretend the star is not accelerating. That's a good way to handle it. Star accel equals particle dot mu index 0 divided by it's just called star mu, so double star mu. Now for size t I equals 1, I less than particles dot n plus I. Here, yeah, this is just gonna be normal. That's just the dt divided by 2, which should be pragma on p parallel 4 size t I plus 1, normal stuff. We're basically just gonna do some computing the distance, and there's gonna be no epsilon involved. Yeah, epsilon's gonna be varyingly not and is involved, so that might cause some issues with the code, but you know, who cares? There's not another 4 in this. So if I go I equals 0, stupid idea. I'm just thinking. Okay, so we just do the basic particles dot n, and no, not that. As you can see, I'm having a bad day thinking. Or rather here. Yeah, here. Okay. So now, what do we do? So you have particles dot velocity is index I plus equals dt divided by 2 times particles dot accelerations index I minus that'd be the distance, so that'd be just the mu times star mu times what is it gonna be? Star mu times particles dot so let's also add a star pause. That's particles dot positions index 0 particle dot positions index 0 minus star pause, and then this is all divided by particles dot star pause, particles dot vec3 d pause. I'm just gonna call it d or d r. Yeah, dr should be particle dot positions index 0 minus star pause. So now if I dr divided by dr dot mag. I think I got this correct. I am going to make sure. So let's clear all this. Let's say, so again, we have our planet here, and you have your star here, and your planet here. Okay, we want the gravity to go this way. So, like, this is 1 0 and this is 0 0. No, it'd be going the subtraction would be doing it this way. So that's not the correct way. It has to be the reverse. Got it. And this is gonna be some interesting decision. You could put it a plus here, and it would flip the direction for you. that's also kind of an interesting solution, but it's not that. That's not the most readable thing. So I'm just gonna. This is the more readable way. Star pause minus particles dot positions index I. So now we have your interaction step is done. Wonderful. Yes, it's. Oh my god, I'm just gonna ignore the Discord ping. Wait a sec, guys. I'm just gonna cut this in 5 seconds. Oh no, it was not a DM. Okay, making sure. Okay, that was good. Okay, so yeah, this should look good as far as that part's concerned. So now we have to do. Now you to transform this, which seems trivial. Transform. So you do have to transform this, which is just saying like. Well, the first we already have Kepler transforms. Well, that's easy. So like, I already coded that, so that's pretty good. The problem is for the Kepler solver. I do not know how to do that properly, quickly. Yeah, okay, so this. What was it again? Transform. That would be inertial to Jacobi. Yeah, you have to convert positions. Oh yeah, right. We need a dummy. Right, we need a dummy thing to throw it in there. Okay, I think you're gonna need another one. Particle store PJ. Okay. Now the problem with that is they're gonna have to initialize it to the size of the particles. That's gonna be a mess. So we just we call an init function. It's just standard business. Okay, so void init dummy store, and we convert a WHFast object, and we just with your particle store particles, and we just very clearly just say if object dot n object dot pj dot n equal is less than particles dot n, we then proceed to just add more. So while pj.n object.pj.n, not that directly, is less than particles.n, we then just, why do we even need this outer loop? Yeah, I'm just gonna keep, we then just say object.pj.add particle, and we just add in the particle, just your default, just like your default. I do not care that it's all junk. It's all being initialized and used anyway. Init dummy store. So if we have, first off, we init dummy store with this and particles. We then proceeded to just now we actually write to it. So pj dot, not all caps, transform, it would be inertial to Jacobi pause particles and pj. Okay. Now we have to solve Kepler's equation. I mean, we do repeat. This bit itself is repeated. And it has it. I don't think the star has moved that either way. I'm just in case, you're going to just grab this and no, not there. At the end here, just in case. And I'll just add a to do here. To do implement Kepler. So yeah, so let's try this. Okay, I'm just gonna, seems like a skeleton for WH, but far less lines than WHFast. So I think it is not the algorithm yet. Definitely isn't the algorithm. Yeah. Okay. Okay, so now, to do, now you have secret. Okay. So now, today needs to use it. Okay. Okay, yes. Okay. I think I'm good on there. Okay, yeah. So, standard way to implement it, you just have to do some monstrosity city, but after the Kepler solver, is it the faster WHFast or the slow WH? Yeah, that's a question I still need a response to, which like iterative method that do not converge, which is pretty common. Okay. This is probably good. Okay, so now, how do I implement the Kepler? The Kepler step, that is something I do need to know, and I am not trying to go into a paper. So, for each Jacobi, prepare initial conditions, set the distance r is equal to this. I think that's that's position, the row's position, and I don't know that. I don't know what to call that one. I forgot the name of that, but that's velocity. Set the radial velocity, set the inverse semi-major axis. Find the universal variable x that satisfies that. Wow. What is S? So what the hell is S? Actually, though, what the hell is S? Okay. So we have delta t equals this, and this. Okay. Set the distance r is this. Radial velocity is this. Okay. For each Jacobi mass, her total interior mass, so for the interior mass, does that include the star? I'm going to assume it does. Actually, it would include the star. Okay, it's gonna be stupid, but it's stupid if it wasn't. Okay. If I go down here, for size t I equals, I'm gonna do the standard method of assuming it isn't, there aren't test particles around, and then trying to adjust with test particles. So okay. Yeah. So now I equals 1. I less than interior, so double interior mu equals star mu. I is less than particles dot n. We then increment I. Okay. I, and at the end we do interior mu plus equals particles dot mu's index I. So now our interior mass, set distance r to equal that. Oh my, too much rust. So it would be double R should equal that, which is equal particles dot positions index I dot mag. Set the radial velocity to equal this. Double VR should equal particles dot position index I times particle dot velocities index I divided by R. Then we set the inverse semi-major axis at that. Okay. So double inverse SMA should equal particle dot positions index I times equals dot. No, that'll be 2 divided by R minus nya of I. So particles of velocities index I with the square magnitude, and then we divide the whole thing by mu, which is the total interior mass, divided by interior mu. What are you doing? What kind of drugs are you on? What's the issue? Invalid binary operands. I wonder how invalid those operands are. Indeed. I swear that it's the radial velocity. Oh, you're right. Yeah, whatever the hell. Oh yeah, that's a dot product. I was interpreting it up weirdly. Dot. Okay. Okay, so now I have the basic variables. I have the stump functions. How do I use them to, calculate Newton-Raphson? The calculate chi. That's a question I need to ask Gemini, and to perform solve chi. Okay, so chi does, if I just solve chi, let's copy this. No one. Okay, let's so square root of mu times dt times alpha, square root of mu. Standard stuff. Say double chi equals square root of mu times dt times alpha times, I could probably, that's better to call this alpha. Double square root mu should equal square root mu. And now we have a loop. 4 into I equals 0, I less than 10, plus I, and you do alpha times chi, and now we make stumpf CS. Double Z is alpha times chi. And now we have just CSX, yay, raw arrays. This is what I like to call peak coding. Yes, okay. Stumpf CS, and if we take CS, combine CS, and we combine with Z, double C equals CS index 0, double S equals CS index 1. I'm not sure what those numbers are supposed to mean. And now we just have that. Okay, that's just a math formula. Okay. This is gonna be easier to code if I just paste that. That's a bunch of math. I don't care if I'm using AI. Okay. D chi, and now we just add this. If fast abs d chi is less than 1e minus 12, break. Yeah, I think that's it. Okay. If I just do mu is not a thing, I'm just gonna say double mu equals particles dot mu's index I. And since it's already being used, may as well just use it here too. Also, I assume these are consts. I don't think they need to be. Okay. Ignoring the billion warnings, that's like basically ridiculous. And so now, okay. Even when Z is 0, which is an issue. Okay, so now F and G series formula. So now that we have chi, so now we just have to here we have to F and G are now have to be calculated here. Okay. Double F equals 1 minus chi times chi divided by R, I think, times the C times the C of A. So that would be Stumpf CS. Yeah, I think we do Stumpf CS. You need to call Stumpf CS again. Great. How great that this is definitely not just gonna be annoying. Double C and double S. And so if we I do double CS, CS6 and call our Stumpf CS Stumpf function. CS with alpha times chi. If we do const double C equals CS index 0, const double S equals CS index 1, and chi divided by R times C. So now we have obtained C and S. This is great. So now if we do now this is now a slightly more complicated one. So double G equals dt minus chi cubed divided by the square root of mu. What? Okay. Mu is the total interior mass. That's stupid. Particles dot mu's index I. Now interior mu here hello, is that the only place where it's actually applied? No, yeah, interior mu is also up here. Yeah, wait, isn't interior mu already defined? What are you doing? Oh, right here, yeah. Let me just okay, so now we just divided by the root mu. So now we time, and now we multiply by S. Finally. And now we have F and G, which means we have our new Jacobi positions, which is pretty good. Therefore means we can do particles dot. So we have pj dot. You know, wait, all of these should have been pj this whole time. Not sure why it's still doing it for ph, but pj. pj. Somewhere here, pj dot there would be positions index I should equal pj dot should equal f times pj dot positioned index I times f is the time derivative. Oh my, what? How? Could you please just show me? I do not know I know what the derivative is, but what? Where? Where is the time? Where is t? There's only delta t, and that's not t. So it means, anyway, pj dot velocity is index I. I'm just gonna put this in here. Please help. Yeah, so please help what is f prime? Prime and d prime. Hilarious comments. Hilarious comments. So yeah, I don't know. Okay, f prime. So f prime is that. Now you need the new distance. Inside your loop after updating that, we then just say our new should equal this. So our new is pj dot position index I dot mag. Okay, you thought just modified index I dot mag. So now f dot equals this. And now we multiply. Now we just copy this. Copy this. Okay. And now we find. Now we store vec3 old v should equal pj dot velocity is index I. Basically, just store things. And now we update this. EJ dot position index I old pre-update. Okay, so we should be using old position as well. We should have an old position as well. No, vec3 old P should equal pj.positions index I. So now I should be able to just paste this line and make a minor modification. So this is not a real variable, but instead I'm just gonna pj dot times old P, and so now is this done? At least the basics. This is done, I'm gonna end the video here, and I'm also just gonna deal with any like the fancy fast stuff like the correctors, which I haven't used so far in here. Okay. Yeah, but now if we do, okay, one final check. Okay, so here we should have, oh yeah, yes, so G times old P. Oh yeah, it also has to be old. Okay, that makes sense. But he didn't tell me that, so. If I just paste this up here, and times G times old V F times old P plus this. And now trying this, hopefully it's close. Okay. Oh yeah, right, I forgot about transforming it back. Right, okay. So now we should be able to determine something in life. Yeah. Okay. Looks close enough. Where do I? Yeah, here. Okay. Jacobi, no, it's transform, Jacobi to inertial particles pj. Oh yeah, and we need to Jacobi to inertial vel particles pj. I forgot to put vel up here. I think it just thinks it automatically as well. I think that's why I didn't complain. But okay, particles pj. Does it know the signature of it? I don't think it does, and I think it just knows that that's proper signature. Okay. Hello? Done. Mass center stability. Yeah, so this is K animation stuff. Correctors, namespace. Alright, looks like it is done. At least the basics. And I'm going to stop the recording here.